Well, good morning, everybody. Thanks for choosing this talk. I know Ben's talk downstairs is awesome. I've seen a version of that before, and you should watch it recorded after you're done with this one. But I really appreciate you coming to this one. My name is Chris Kelly, as it was mentioned, and on the internet I go by Amateur Human, so that's like on Twitter, GitHub, things like that. You're welcome to harass me on any of those at any time. I work at a company called Relic. We do, for those who don't know what we do, is application performance monitoring. So that's really where this talk started, was something that we encountered doing an upgrade, and we'll go over that a little bit. But Relic actually really loves Australia. We actually have 3 Aussies that are on staff, some of the most brilliant people I've met. So 2 of them work in the US, and 1 still lives here. And so much so that we love Australians that we put one of them on the homepage. So that is Julian. That's the back of his head. That's the best we could do. That's amazing. So I'm also having a great time in Australia. This koala's name is actually Ruby, which is awesome. I walk into this thing and I'm like, yeah, this is Ruby. I'm like, are you kidding me? I'm here for Ruby. I'm like, this couldn't be more perfect. So yeah, that was at the Sydney Zoo earlier this week. So thank you for having me. It's been a great time so far. I'm definitely coming back. This is my first time. So let's dive into what we're talking about today. There's going to be 4 parts. The first part is really kind of what is really going on. What is garbage collection? How did we get here with this talk? And things like that. Next, we're going to kind of look at how to navigate the C Ruby. Because what we're talking about here is C Ruby. We're not talking about Rubinius. We're not talking about J Ruby or any other implementation. We're actually talking about C Ruby. And has anyone ever opened? How many people have opened a C or header file in the Ruby source? How many people close it the very second they open it? So the idea of part 2 is to hopefully get you comfortable looking at the source code and kind of what it means. Because in part 3, we're really going to we're going to deep dive into basically once an object gets created all the way through garbage collection. So we're going to walk that code. So there is probably 10 lines of Ruby in this talk and a couple hundred lines of C. And the Ruby isn't interesting, it's just fake code to do stuff for me. So be prepared, but we'll get through it together. I had to get through it, so. And then finally, we're going to talk about garbage collection in general. So looking at what 1.8 did, the changes that we made in 1.9, and then how we're going forward in 2.0. So that's kind of where we're going. So you know, once you create objects, then you've got to get rid of them. So that's sort of the path we're going to go on. Hope that sounds good to everybody. So what are we talking about? As I said, we're talking about C Ruby. There are great other implementations of Ruby, but in this case, we're building on mapped MRI, right? So Charles is here, who leads the JRuby team, and does awesome work using the JVM garbage collector. Unfortunately, C Ruby doesn't have that benefit of using the garbage collector out of the JVM. So we have to figure out how to do garbage collection on our own. And that's one of the more interesting components of this, what I think I learned through this talk, is how basically the core team moved from the 1.8 kind of doing garbage collection on their own towards 2, where they're starting to use techniques out of the Unix processes that handle garbage collection for them. So really kind of working on that. So if you don't know what garbage collection is, hopefully you do, otherwise you're really confused why you're in this talk. Garbage collection is a matter of automatically finding unused memory and reclaiming it so it can be reused by another process. That's basically all it is. So all of this started way back in September. Relic was running Ruby 1.8, and that's what it looked like. So the bottom section is garbage collection time. So we were running about 80 milliseconds in garbage collection time for the main application that you're going to log into. The middle chunk is just the Ruby process itself running, minus garbage collection, and then the top is the database call. So in September, we're like, hey, we need to get over to 1.9 because we're trying to get on, you know, advanced things. We happen to be a performance company. We think we should stay up to date. So September of last year doesn't seem like too late to get on to 1.9, given the fact that 2.0 is coming out in a couple days. So we moved over to 1.9, and we saw a dramatic drop. Our average garbage collection time moved to 42 milliseconds. So internally, that got us thinking about what is going on about garbage collection in 1.8 and 1.9. So This actually started with one of the engineers that you saw on that slide with Tom Lee. He started doing explorations, and he and I got talking. I'm like, hey, that's an awesome thing to talk about. Can I steal your idea and make a talk out of it? And so I did. So this is how I got here. If you want to see what that looks like, you can see the comparison. So we are saving a little bit in the Ruby process. The Ruby process is a little more performing, so that entire gap you're seeing isn't entirely garbage collection savings, but you are saving a good amount of time. You're saving roughly 48%, so you should operate now, right? But there are caveats, so make sure there are some restrictions there. All right, so that's how we got here. Now, let's talk about Ruby. Ruby is all about objects. Everywhere, everything, everything's an object. Garbage collection is about objects too. Objects get created by Ruby, and then you have to collect them again. So the major function is to gather up everything that's unused, and it's going to walk through the tree, and we'll go through this a little bit. It's going to walk through the tree of all the objects that are created and then bring them back in for another process. It's considered garbage if it's reachable. It's not garbage if it's not reachable from the root, and we'll talk about that. So there's a thing called ObjectSpace. ObjectSpace is a module in Ruby that gives you access to every live object that exists, so every object that's been created, and then you can traverse that using an each object method. You can send in things like each object class, and it'll give you every class that gets created in your program. So it's very handy. This is where garbage collection happens. You can call a garbage collector off of this. You might have also seen something like gcstart. That's basically the same thing. ObjectSpace.GarbageCollect and gcstart are doing basically the same thing. So I created a little program. I just literally ran ObjectSpace.CountObjects in a file, and this is what I get. So I get a big hash full of everything that gets created. So when Ruby starts up, this is what you get. You can see we already have 14,000 objects created. This isn't Rails, this is just Ruby. Imagine how many objects get created when Rails starts, because it has to create it has to load every bit of code that goes into your object space. It has to load every variable up, so all the environments, all of that stuff is given to your object space. So you can see your object space can get really big very, very fast. So the first thing we want to look at just real quick is what happens when you create a class, right? So first we're going to take a look at classes. We have 478 classes out of the box. If I create a custom one, which is oops, class.new, I get 2 more. So clearly, creating classes, I get magically 2. And we'll get into a little bit more about that. So I'm already starting to gather up all of this stuff. Next, let's actually create an array, right? So just an empty array, just an object array. I get an array just like I expected, 1 more. Everything seems to be going along normal. Now let's actually fill it with stuff. I start with 8 objects. I'm going to put 10,000 foo objects inside of that array. I've got 10,008 objects. Kind of expected, right? So then we continue on. Now I'm going to try to collect some garbage, right? I haven't done anything. This is all I'm doing so far. Nothing changes. So clearly I've created 10,000 objects. The process is still running. So those 10,000 objects are considered live and reachable still. So when I try to collect garbage on them, nothing happens. So let's empty the array. Reset it back to 0. And I run it again without garbage collection first. I see those objects are still considered live and available, or alive and reachable, so we haven't got anything. So let's run some garbage collection real quick and see what happens. Pretty much exactly what you expect. You lose all 10,000 of them. They're now available back through the process again. Let's look at our class again. So we have that 480, we started with 478. I'm going to go ahead and delete, I'm going to remove that class, and the only way you can do that, removing a class or a constant is something you shouldn't do. It is a private method, so you have to use the send. So we're going to remove constant off the object, and then collect that, and then we get back to where we started, 478. That is garbage collection. That is in a very simple program, creating and destroying things, and that's what's going on. So now imagine with this sort of 10 lines of code, this is basically the only Ruby code you'll see again and again. Imagine what Rails does when it boots up, and how much objects it creates, and how important garbage collection ends up being. Because at some point, your processors or your computers run out of memory, right? Especially if you're doing embedded systems, like Matt's is working on in Ruby a lot, and that's a lot of small embedded systems. There's not a lot of memory space on there, so garbage collection is actually an extremely important thing. So let's navigate some C Ruby. Let's take a look and poke around what's going on in there. So Ruby is written in C, as you might know. So the things we're going to look at today are here. So we're looking at a header file, which contains most of the things we need. We're going to look at the VM a little bit. We need to call that a couple times, and then the object and garbage collector source files. That's basically all we're going to need to kind of traverse object creation and garbage collection. That's it. So first thing you need to know about C Ruby is how to read it and understand what things are. So value is usually an unsigned long, and we'll get into that in a second. It's a pointer to Ruby objects. So inside of memory, everything is being pointed to through this value macro. So in C Ruby, they use very, very heavy macros. If you're not a C programmer and you're not familiar with macros, you're looking around like, what the hell is going on with this? So anything capitalized is generally a macro. Value is a macro to get the pointer for this R object that we created. Pretty simple. Other things that, and here's where the trick comes in, and we'll talk about macros in a second. Value is usually a pointer, but there are certain things that value represents that aren't pointers, they're actually the objects themselves. Things like true, false, nil. Those things are used so often, it would actually be very expensive for the process to actually get a pointer and then go get a second memory allocation and make a second memory slot to look up nil every time nil is called or true is called. So the trick that the core team is using is this macro value is actually returning either the pointer, or if it happens in one of these special cases, it's returning that embedded in the in that pointer object itself. So it's not making a second trick, it's actually returning the entire object at that time. I found that to be terribly clever, and we'll see another use of that in a second, and hopefully it becomes a little more clear. So there are lots of object types. You're probably familiar with all of these. They look pretty familiar. So we can create a basic object is we're looking at Ruby 1.9 mostly. So in 1.9 and 2, we're looking at basic objects, and then there's everything, strings, classes, all those things. So we can create those. So we were creating with foo.new, we were creating just basic objects, plain old Ruby objects. So this is what you're getting. This is what is being called when you're using plain old Ruby objects. So what we have here is a struct of a basic. That's going to include a pointer to some flags and a pointer to the class. So in our case, foo was the class. So that pointer is going to another object called another our class, which is foo. Below that, we can see that we embed RBasic into our object, right? So everything that is an object in Ruby has RBasic as an ancestor. That's how we do that. So if you looked at RString, you're going to see the same struct RBasic basic. You're going to see that in every one of the Ruby objects. Secondarily, then we end up getting a couple other things. We're going to get a number of instance variables. That's what that is sort of cryptically saying. And one of my favorite things about C code is how terse it is, and how cryptic things are, and it blows my mind. Especially coming from Ruby, where we name things very verbosely. So then we also have the instance variable pointer. So that's actually pointing towards our all the instance variables we have associated with that class. And then something that's interesting, and we'll get into this in a second, is that second value array. And we'll talk a little about that in one more second. It's a little easier to map this to kind of look like this. This is what an object kind of looks like. So you have this value pointer that's going to our object, which contains our basic, which has flags. The flags are what is going to become really important for us in a few minutes, is where Ruby tracks whether it's marked for collection, if it's frozen, so if you've got a lock on it, things like that. So we have class, and then you kind of get a sense of the other components that are part of typical Ruby classes. So hopefully that looks pretty clear, kind of getting a visual map of what's going on. So let's talk about macros, because you can't talk about Ruby source without talking about macros. So a macro is really just a substitution. So what it's doing is taking the values being passed to it and substituting in another chunk of code illustrated above. They're used extensively, so get used to seeing them and understanding how to read them. And almost always, the value pointer, as I mentioned, the value pointer returns a pointer, but not always. So that's where this macro comes into play. So let's look at some macro magic. So first, this is our string, right? So we've got our RBasic, pretty used to seeing that now. Then we have something that's really interesting beyond that. The Ruby core team has done a performance improvement for our string. So Pat Chauncey, thank you, did a nice write-up on this, talking about how strings less than 23 characters are more performant than strings over 23 characters. And in that case, it's because what's happening is the core team is embedding the string data into this object itself, much like that value pointer is embedding true or nil into that object itself. And we're doing the same exact thing here. So this trick, and the way they're going to get that data back out is using a macro. Because if we look at it, let's look through this real quick. So we've got this union. That union is combining two things, either this struct that we're naming heap, and that struct contains a bunch of pointers that are going to actual string values later. So this is where a string that is 24 characters or above would be identified in this object. Or if it's 23 or less, then we end up with actually saving the array directly into the object itself. So you can imagine if you're writing code to retrieve this value, that could be pretty hairy, right? So we're going to end up using a macro instead. So let's start towards the middle. So we're using an RString pointer macro. So anytime you're trying to get a pointer back for a string, you're using this RString pointer. And what that's doing, it's going to run this code. So you're passing the string in. It's going to run the RBasic macro on it. Again, so you can see how many macros are being used in this exact scenario. So you're using RBasic macro to get the string and retrieve the flags out of it. So that's going to tell us whether it's marked for collection, if it's an embedded object. So in this case, if it's 23 or less, that data is embedded directly in it. If it's not, that flag is not set. So if that flag is set, then we move on to the second line, where we see we're going to retrieve it out of the array portion of the object itself. If it's not, then we're going to pull it out of the heap and pull the pointer for it. So either way, this is returning a pointer, but it's returning in two different ways. And the developer doesn't have to care where it's actually being stored. As a developer, if I'm working on another chunk of C Ruby, all I have to know is use RString pointer macro, and I can get the pointer back for the string, regardless of where it's stored. And someone else can do efficient and performant work on that chunk of code. I mean, I saw that, and I was like, holy crap, that's amazing. That's using, 15 years ago when I was doing any meaningful amount of C, I wasn't nearly that thoughtful about how to make my code flexible, how to do anything really terribly interesting with it. So I saw that and it kind of like clicked with me that this is something serious that's going on here. So, again, the reason this is important is because you're not making those round trips, right? The performance benefit comes from either just getting the object data itself on that above line, on the as array, or having to make a second trip to get the pointer and then go get the data itself. Hope that makes sense. So, if we weren't using a macro, if we substituted this all out the way it works, this is basically what a developer would have to write, right? You have to cast the RString string back and then get the pointer. Or write the code that then determines if it's in the array instead of the pointer itself. So we're using macros so we don't have to write this everywhere and all the conditional logic to hunt things down. And it makes life a lot easier. So the last bit about C Ruby that you kind of have to understand before we can get into much more is how heaps work. So on the right side, your left, we have the process, all the memory allocated to this process. So that includes things like operating system, virtual machine, your program code, all of that gets put into memory. Then there's a chunk of memory called Ruby Heaps with an S. Those heaps are then allocated into slots. This is terribly complicated. Those slots then point to a heap themselves, singular. That heap is an array of pointers. So you can see that basically how we work through is there's a larger chunk of data, a larger chunk of memory that's being allocated to a heap. That heap is a defined amount of space available to it, and then we assign individual pointers that point to other memory itself. I'm not sure if that's helpful. I think, so what's important here is during certain kinds of garbage collection, what happens is you can either allocate new heaps, say the gold ones, or you can garbage collect inside the heap itself, clear that up, and things like that. So there are multiple things the garbage collector has to decide to do. Whether if you've allocated all of your heaps, the plural, then it has to go find garbage collector. the garbage collector can't collect any new objects, then you have a memory error. You're out of memory at that point. So, that's it. Everybody ready to dive into some code? Yeah. So, this is where the rabbit hole begins. And this is sort of where the title for the talk came from, because if you start down this path, it's ugly. It gets ugly real quick. So, the very first thing that happens on foo.new, right, we call the class new method. And that's calling a method called RBClassNewInstance. Seems pretty basic. What we really are interested in here, though, is allocating an object. So that's where we go to next. First, we try to create an object, then it needs to allocate some memory for it. So let's go over to object allocation. Here, the asterisks and dots are cut out things that are either irrelevant. Oftentimes, they're error checks to make sure things are being set properly when they are. So you're not missing anything by looking at this. So the first thing that happens is we look at RBObjAllocate and Alloc. What we need to do there is get the allocator for that class. Every class has a different kind of allocator. So we actually assign allocator to getAlloc function for the class that we're passing in. So in our case is foo. And foo is a RObject, which is also a basic object, right? So we need to find where the alloc function gets defined, right? So we keep digging down to these methods, or we're chasing this down. We end up getting to a point where we assign the allocator from an allocator pointer here. So we're using another macro to find the to pull out the class and then find the allocator for it. So where is this defined? Where does the pointer for allocator get defined? That's in, lo and behold, RBDefine Alloc function. So we can see that we're defining it based by passing in this function into the upper function and then allocating, or assigning it. Pretty simple. Everyone's pretty clear so far. We're just kind of chasing this down and we're just working our way through. So where does that get defined? So we hunt this down, you know, app is your friend. We see that in a init object, which is a method or a function that gets called to basically initialize part of Ruby. Basic object is getting its function that's being passed to it to allocate things, right? We're trying to pass in a function and assign it to the allocator. Is RBClassAllocateInstance. All of that to get basically back to where we could have thought about it. But these are well thought out processes like the macros that are used to make C Ruby extensible and extendable and flexible. And so playing nicely with the way it works is the best step. So now let's dive into RBClassAllocateInstance. Okay, we found ourselves another macro. Exciting. We love these macros. So all that's doing is taking a bunch of parameters and passing them off to a macro. Let's look at our macro substitution. And we're doing new object of, and this is where I cheat on the top of my title talk, because we actually never call RBNewObj. We actually call RBNewObj of. It just doesn't have the same ring to it. So I kind of cheated on that. But in the end, the macro is passing off the class and the flags over to RBNewObj of. So let's hunt that down. And here we are. Now we're wrapped inside of RBNewObj of, and we're calling newObj. The reason that there's all of these like layered points is that you need to make sure that the memory you're allocating is put into the object space so that the Ruby process can then go collect it later. If you circumvented some of this, if you just call newObj itself, and you didn't do it in one of these Ruby wrappers, then the Ruby process would have no idea it existed and never be able to collect it. So you would have a memory that you created yourself, because nothing, unless you happen to do your own garbage collection with it, that's your business. But if you want to use Ruby's internal garbage collection, you have to be nice and use the wrappers that go around these things. So we're doing some more allocation. So here we are. This is a pretty long one. We're going to go through this in a couple steps. So newObj is really where the magic happens. We're finally there to create an object. So let's first start getting our object space, which we need to access the object space. We're going to pass that in and hold on to it for a bit. Then we're going to try to do some garbage collection. So this is, we're just kind of working our way down through the code. Right here, we do garbage collection. I'm not going to get into this just yet because that sort of will sidetrack us too far. We're going to assume garbage collection happened properly, or nothing interesting needed to happen in garbage collection. So we're still trying to allocate our object. Garbage collection says, hey, I'm good. We're going to move along. then we end up saying, we're looking at our object space. This is where this becomes important. So object space has pointers of free list. This is a pointer that says, this is the next object available. This is the next object pointer available. So assign it to object, then go get the next one after that, because it's got a pointer to free next. That's going to give you another object space, and assign it to free list, right? So we basically just swapped what's the next available pointer, so that we can keep doing this over and over. So now we've got object, which is a pointer to the next available space, which is great. And here we are. We've got a macro for mem0, so that's basically taking the object that we have, that pointer that we have, and clearing it out, because it's got garbage in it right now. So we're going to empty that out and make it 0. We're going to iterate the number of total objects we've got created, and then we're actually going to just return the object. That's it. We've created a Ruby object. All of that. So we've created this Ruby object. Now, let's step back to garbage collection. What's happening in there? Garbage collection is kind of complex. There's lots of checks inside of it. The thing that, if you want to dig into the garbage collection chunk, I want you to be prepared to fight with sort of these inverse true-false statements that are everywhere. They're littered in it. So you have this ready to garbage collect not, but if you dug into that, it actually is going to return false in some cases. When you think it's supposed to return true to make it all logical, like, is it ready to garbage collect? Yes. Well, actually, ready to garbage collect needs to return false in order to do it properly. So if I'm going to do anything with garbage collection in the next couple weeks, it's going to be to refactor this code so it reads logically. Because it broke my brain for a good solid hour. So we do a couple checks to make sure things are okay. And then here's where we get to some interesting stuff. So first we do during GC, so we're iterating that to increment it 1 up. So that basically tells the world, hey, we're doing garbage collection now, you can't do anything. There's lots of checks all over Ruby code to see if you're in the middle of garbage collection. You can't do other garbage collection, you can't do object assign, you can't do object allocation. It's stopping the world from acting. So that's what that's doing. So the second you start garbage collection, that's where you're seeing that hiccup, is because of that line of code that says stop. Then we're going to do a method called marks and a method called GC sweep, and a function, sorry, C. And those are just iterator loops that are going to go through everything. It's easier if we don't look at the code for those because they're just these while loops, and we're going to talk about what mark and sweep is, but I want to show you where they come in. And then once those mark and sweep are done, then we return true and we're all happy. So we've done our garbage collection process, and our application performance has stopped, basically, because we told it to stop until it returns back out of this. Okay, so now we're on the garbage collection itself. So let's create a bunch of objects again. Nothing special. We've done something a little different here. All we've done is created a second empty array, added 1 object to it, and then we have our 10,000 items again. So in a virtual space, this is what your object allocation is looking like. You have a set that's called root, and that's where everything that, all the pointers that get created, and then anything that's a descendant of that gets put into the heap. So you have these pointers in the root that are pointing to actual objects themselves. An allocated object is in the live set, and these are just phrases you're going to have to get used to. Unallocated objects are in the free set. So what we're doing is pulling from the free set and moving them to the live set. Well-known objects are in the root set, so that means that they went through the proper channels to be assigned into the root set and then are basically findable in ObjectSpace. What we want to do in garbage collection is find all the unreachable subset of the live set. We don't have that yet. Everything is reachable from the root out, so we're good. Hopefully that makes sense. This is another way to look at it. So we've got the heap, right? We talked about that. So there's the heaps slots. Here's a heap slot itself, individual ones with the objects. Inside, all the way into the flags, is this flag called fallmark. That's where the mark and sweep component comes into. What happens during garbage collection is that we walk through all the objects available, we mark the ones, and then we sweep them away. We sweep the ones that aren't marked, and we'll see what that looks like. So let's actually disconnect something from the root. So we're just going to nil out that objects array, and now you can see this is virtually what it would look like, is that we don't have any connection from the root into the heap. So let's do the mark phase. We're going to walk through everything that's reachable from the root set, and then work our way through it. So we'll start at the root, find any descendants it has, mark those objects, move on to any descendants those have, mark those objects, and so on and so forth, until we're done. And then we start back at the next object in the root, and work our way through. So in the end, if we did that, we would end up looking like this. So all these FL marked flags on these 3 objects have been marked. The other ones are empty. Now it's time for the sweep phase. Sweep is we're going to traverse every object in the object space, and then unmark the ones that are marked, and then remove the ones that didn't have any marks. And so what happens is we walk through the heap side of the memory set now, unmark all those because we basically have said we've seen these, they're good to go, they're going to stay. Unmark them so that the next time garbage collection runs, it can walk through that and make sure they're still reachable. And then if it's not marked, then we're going to remove it. So this is what our application looks like now. So as I said, mark and sweep, this garbage collection that we have now, is basically stop the world. Nothing can happen because we don't know what is available to be used at the time. So it locks all the processes out, making mark and sweep somewhat a performance hit. The big performance hit comes because you have to touch every object at least once, and some objects twice. The application or the process has to run over and see if it needs to be marked on everything, and then then it's going to check everything again, see if it has a mark. So the top ones were touched twice, and the bottom ones were touched once, and that's where we come to the problem. And so our memory or our process time is directly related to the number of objects we create, and that's where the big hurdle comes from. So how do we mitigate that? So this is what this classic form of mark and sweep is what Ruby 1.8 mostly looks like. In Ruby 1.9, Nari introduced lazy sweep. Lazy sweep only runs in case there are no free objects or the heap. You can't add another heap slot. That's the only time lazy sweep runs. Now that's okay, but ordinary mark and sweep is costly. Lazy sweep's no less costly. It just runs less often. That's not the best solution. So what do we do if now we're stuck? We're on 1.9 and we've got this less than frequent version of garbage collection. So there are some other garbage collection techniques. There's copy on write is a classic one. Copy on write is a Unix process, built into the Unix process, and it's how Unix and Unix-like systems do garbage collection themselves. So when a process is forked, the memory allocation isn't copied. It's only copied when each process is running. It touches the memory itself. So we've got process A running with heap A as its memory, process B with heap B as its memory. And as these things process requests, do form data, whatever they're doing, they're going to use their own memory set. But when the process was forked, everything that was currently in memory gets to sit in shared memory until one of those 2 processes touches it again. Once it rewrites it, then it has to move it into that process itself. So what happens though is we get a little stuck, because process A is going to run its garbage collection and process B is going to run its garbage collection on any memory it has access to. So process A runs through its garbage collection. It's got access to those over there. They get marked, and then the one in the shared heap gets marked as well. Well, marking it modifies the FL mark flag, therefore changing that object, and now B is no longer allowed to touch it. Because it's no longer shared memory, now it belongs to A. So now it looks like that. So there's really no shared memory at all, because the garbage collector is running all the time. Every time memory gets allocated, anytime an object is created, garbage collector checks to see if it needs to do something. So copy on write doesn't work in the way C-Ruby is currently configured. So the wonderful Nari continued on his quest to improve the world. Started with bitmap marking. Bitmap marking moves the FL mark flag out of the object itself and into a new construct. So this is what the new heap looks like in Ruby 2. So the heap has a header on it now that maintains a bitmap of all of the marks, all the collection marks for the objects in that heap. So now if process A is running, and it runs across an object, and it needs to change this marked flag. It's changing the header, it's not changing the object itself. So now we have shared memory again. Now we can get back into doing things that are more important and let pre-built systems that are designed and performant on garbage collection do it. You know, JRuby gets the benefit of lots and lots of hard work from brilliant people on the JVM's garbage collector. Now we get some help too. Thank goodness. So, now what? What do you do now? The idea here was to give you an introduction that this stuff isn't nearly as scary as it looks at first. Garbage collection is terribly interesting. At least it became terribly interesting as I worked on this over the last few months. I wanted to give you some resources. So there's a great paper on garbage collection techniques. It's pretty old, but it's wonderful. Talks about some experimental ones, including it starts with mark and sweep, and it talks about bitmap. So maybe this is where we'll go next. After bitmap doesn't work or we need more performance, we'll look at other garbage collection models, so we'll do that. And these slides will be up on speaker deck, so you don't have to write these down. And I want to thank the people that really kind of built the infrastructure around this talk. So these are some of their resources. So Nari ended up doing basically all the work on garbage collection since winning. So if you ever run into him, you should thank him, because nobody else is really working on that chunk. Then we've got the Ruby Hackers Guide, which is a great resource. It's old, but that's terribly available now, and it used to be only in Japanese. Now it's a good chunk of it's available in English, so that's a great place to start. Then PAX Ruby under a microscope is a great place to start looking at C and how Ruby interacts with C. It doesn't get into garbage collection or too much memory management, but he does have some blogs that talk on it as well, so check out his stuff. And then the classic C book on if you don't know much C or you want to kind of refresh your brain on how pointers work, basically, and macros. That's a great place to do that. So thank you. And I'm happy to take questions. We've got a few minutes left.